So good afternoon, everybody, and thank you for attending our fifth Australasian Fluid Mechanics seminar. Today's speaker is Professor Peter Jordan, who's very graciously woken up quite early to give a presentation. It's 8 a.m. over there. Professor Jordan was born in Ireland, and he has since then made his home in France. He did his undergraduate degrees and his PhD at Trinity College in Dublin, and he's been at University of Poitiers since 2001 now. And his research interests are in aeroacoustics, turbulence, and instabilities. And he's done some collaborations with people at Monash University and also with members of the fluid mechanics community in the US as well. So thank you very much for giving us this talk, Peter.
Thanks, Sean. Sorry, go ahead.
Sorry, I was just going to say to everyone, before we start, please make sure that your videos are off and your microphones are off, and then we would be happy to accommodate your questions at the end if you raise your hand or if you post something in the chat. Thanks, Peter.
Okay, thanks, Sean, for the introduction, and thanks for the invitation. Good morning, well, no, I guess good afternoon, everybody. So in principle, for the next 45 minutes, you should only be hearing from me. There is, of course, the possibility of brief interruptions from either of my two kids, both of whom deserve credit, of course, for their contributions in the preparation of these slides during lockdown. So I'm going to talk about linear modeling. Last night, I decided to add a plus to this because, as you'll see, it's always linear plus something else, something to account for nonlinearity. So the talk is organized like this. I'm going to give a brief history of what we call coherent structures and turbulent shear flow. And then I'll basically get into 4 chapters of the talk where I'll talk about recent results and developments that I've been involved in recently. So the history, I've got about 5 slides on this. The first observation, I think, of coherent structures in turbulent shear flow in general should be credited to this guy, Erik Møller-Christensen, who's a prof at MIT. Here he put 2 microphones in the hydrodynamic pressure field of a turbulent jet, and he saw these wavy signatures extended over scales much greater than the integral scales of the turbulence. And so based on that, he suggested that we possibly need a new way of looking at turbulence with respect to these regular patterns. And I guess this talk is all about this new way of looking at turbulent shear flow. The first linear model, I think, where there was a calculation, a stability calculation done and confronted with experimental data, I think it's due to Krohn-Champagne. They looked at natural and forced turbulent jets. So there's a picture here on the top. From these, they extracted the organized structures, and I guess on this bottom plot, this is the one data point that they trusted enough to put on this figure that shows growth rate as a function of wave number. So there's the data point, and these lines correspond to local stability analysis. One is temporal, the other is spatial. So that's a first indication that stability theory can roughly describe some of the characteristics of these structures that we see in turbulent jets. And I've cited Crichton and Gastra here. Basically what they did was they extended the local analysis to a weakly non-parallel scenario using a multiple scales approach. So this is a WKB type approach. The data points on this plot come from Krohn-Champagne. So now we're looking at wavelength of the organized structures as a function of frequency. One of these lines is the locally parallel analysis. The other is the weakly non-parallel analysis. And you can see again that there's a nice match between this simplified theory and the data from the turbulent jet. But I guess I'm citing them less for the result than for this, this citation here, which is a kind of an ad hoc justification of why you might do this. They suggest that it possibly makes sense to think about instability of the mean velocity profiles on the basis that turbulence somehow establishes a kind of equivalent laminar profile where these large-scale organized structures are concerned. So this, I think, is the first mention of the role of turbulence in this kind of modeling. And as we'll see in the talk, the role of turbulence the role attributed to turbulence has changed quite some in recent years. So this slide shows the evolution of what I'm calling homogeneous models. What I mean by that is you take the Navier-Stokes system up here on the right. Can you guys see the mouse, the pointer? Somebody could confirm that would be useful.
Yes.
Okay. So this is the Navier-Stokes system. You take the dependent variables, perform a Reynolds decomposition, so mean and fluctuation. You then linearize about the mean. That gives you this operator L here. And this linearized system, LQ prime equal to 0. And this is the thing that you hope will be useful for describing these organized motions. So you can formulate this in a locally parallel framework, weakly non-parallel as per Crichton and Gaster. There are various ways of parabolizing the linearized system. The most rigorous of these has been proposed by Aaron Town and Tim Polonius some years ago. And today it's possible to do global analysis for fully 3D mean flows. So here I'm just showing an example of a comparison between a homogeneous linearized system and experiment. This is taken from André Cavalieri's PhD thesis. We're looking at, for each of these plots, you're looking for a given frequency at the power spectral density of velocity fluctuations on the center line of a turbulent jet. The squares correspond to measurements, and the black lines are what you obtain with PSE. So it's a solution of this linearized system. And so you see that you get a very nice description of the growth phase of these organized structures up to the point at which the flow becomes locally convectively stable. A couple of years ago, myself and Tim Polonius wrote a review on basically how well these linearized systems can describe coherent structures in turbulent jets, and in particular the sound that they generate. So I'm going to move on to inhomogeneous models, but before I do that, just a word on local analysis. It's great, of course, that we can do global analysis now, but local analysis nonetheless remains an extremely useful tool. And I'm showing an example here from a recent study by Daniel Edgington, Mitchell, and others, where he's extracted modes from a supersonic jet, an underexpanded supersonic jet, which is in a resonant condition that we call screech. And if the video would play again, you'll see these modes moving. So things moving upstream and downstream. These are basically the K plus and K minus modes. So the downstream and upstream propagating modes that couple to create the resonance. And so what we've done here is for the upstream traveling mode, which previously was attributed to free stream acoustic disturbances, you can see that it's concentrated within the jet. And if you take a radial slice of the data as extracted from the PIV measurements, you see this black line. So this is velocity fluctuation amplitude as a function of radial position. And this red curve you're seeing comes from a vortex sheet model, in fact. So this is a local analysis, which helps us to put names on these things. And in a similar manner, you can understand that the downstream traveling mode here is a Kelvin-Helmholtz instability. And so this vortex sheet model is also the basis for a very simple model that allows you to predict the evolution of the frequency of these global modes as a function of operating conditions. So the colors on this plot show peaks in the power spectral density as a function of Mach number, and the black lines are predictions constructed from a vortex sheet model. So it's nice to be able to do global analysis, but very often the local analysis is the thing that allows you to really discuss and interpret the physics. So it's good for the construction of simplified models, interpreting not only the data, but also the global modes. It's great to be able to compute global modes, but sometimes it's not entirely clear what they are or how they work, and the local analysis can be very helpful in that regard. And I like very much this citation from Patrick Huer, which says compute global because we can. But continue to think local, because very often that's where the physics is happening. So I now want to discuss in this slide what I'm calling inhomogeneous models. So what I mean here is, again, you take the Navier-Stokes system, you do your Reynolds decomposition, linearize about the mean, but rather than throwing away the nonlinear terms, you retain them on the right-hand side. And so you can now read this system in an input-output form if you invert this linear operator, and it becomes known as the resultant operator. And so this is also a useful way to analyze and describe coherent structures in turbulent shear flow. So in terms of the evolution of this, the first person to do this to the Navier-Stokes system was James Lighthill in 1952, where he did it for the purpose of describing sound generation mechanisms. And in the evolution of what's called the acoustic analogy between Lighthill and the more recent models of Goldstein, basically what you're seeing are different ways of rearranging the Navier-Stokes system into a linear left-hand side and a nonlinear right-hand side. And the different rearrangements come from using different base states or using different dependent variables. The first application in analysis of turbulent flows, I think, or at least for a description of turbulent mechanisms, I think should be credited to Landau in 1967. And there's also this interesting paper by Farrell and Yanu in 93, where they talk about stochastic forcing of the linearized Navier-Stokes system. More recently, this is referred to as resultant analysis, and it's finding very broad application in problems ranging from channel or pipe flow to high Reynolds number compressible turbulent jets. Just last year, we wrote a review on the utility of this kind of modeling for the dynamics of jets and their sound with André Cavalieri and Lutz Lessach. And here I just have an example of a comparison with experiment. This top plot is showing you a streamwise radial slice through a jet. This is a spectral POD mode that's been extracted from this at some given frequency. You see this wavy pattern that we refer to as a wave packet. And if you compare this with the leading singular modes of this inverted linear operator, the resultant operator, you see that it provides a very nice description of what we see in the experiment. If you then reduce the frequency and look at higher order azimuthal modes, you see these streaky structures. This was done by Petronio Nogueira and others last year. And this is showing, again, these modes come from the linear operator. They compare very nicely with the experiments that we performed. And this basically showed us that the lift-up mechanism that we're more used to thinking about in wall-bounded flows is also active in turbulent jets. Okay, so that's the short history, and that brings me into the first of the studies I'd like to discuss, which talks about an ambiguity issue, which we discovered last year, or I guess it was last year, but in fact I should say we rediscovered it, because in fact this is something that we knew already from aeroacoustics. I'll talk a little bit more about that as we progress through this. The work was led, and the heavy lifting was really done by Ur Carbon, who's a postdoc working with us in Poitiers. And this was funded by the European Union through the Clean Sky 2 program. So here we go. Again, this is an Navier-Stokes system on the top. You build a Jacobian, evaluate that thing at the mean flow, and that gives you this operator A, which describes the linearized dynamics. You retain the nonlinear terms, and we call this some external forcing F. If you discretize that system, write it in frequency space, it gives you these equations. So in all of the results that I showed in the introductory part of the talk, we're relying very much on the matrices A or to analyze or describe coherent structures. So the question that we were faced with in the study that we did was, well, we know from aeroacoustics that the way you split the system into left-hand side and right-hand side is ad hoc, it's arbitrary in fact. So the question we asked here is, well, what happens if we change either the linearization point or indeed the dependent variables? And in fact, that's something that's done in aeroacoustics. The different acoustic analogies often differ in terms of the dependent variable that's considered. Lighthill considered density, others considered pressure, Lilly considered the logarithm of pressure. Then people talked about using enthalpy, total fluctuating enthalpy. And so each time you change the dependent variables, you're basically changing the way you split the Navier-Stokes system into a linear piece and a nonlinear piece. So we're interested in what the implications of that might be. So to look at that, we consider a nonlinear variable transform from some original set of variables Q to some transformed set of variables Qt. And an example of a nonlinear transform would, of course, be the change from primitive to conservative. So in terms of the transformed variables, the Navier-Stokes system and its linearization look like this. Again, you discretize, write it in frequency space, and you end up with these equations. So the question then is, under the nonlinear variable transformation, do these two systems tell the same story? That's what we're interested in exploring here. Of course, both systems are exact, and so they should or they will tell the same story, but that of course depends on you having access to the right-hand side. And that's something which is problematic. F or ft are difficult things to extract, be it from experiment or numerical simulation at high Reynolds number. And so frequently they're either neglected, in which case you have the homogeneous problem, or they're very highly simplified, as is frequently the case in resultant analysis, where we think about these as being quite in space and or in time. And so in that situation, you're relying to a large degree on the properties of the matrices A and R to provide a description of the phenomena you're interested in, and you're relying on these to tell you the story about the physics. So the question is, do these things, or can these matrices change with a change of variables? So this is how we went about exploring this. The first equation is simply the nonlinear variable transformation from one set of variables to the other. If you take the time derivative of that thing, it gives you a relationship between the Navier-Stokes system in the transform variables and the Navier-Stokes system in the original variables. We then compute the Jacobian. So on the left-hand side, you're differentiating with respect to qt. On the right-hand side, with respect to the transform of q. That gives you this system. And of course, what we're aiming for here is to write down an expression which would give us a relationship between the operator at and the operator a. Now, it turns out that that's not as straightforward as we would have liked, because when you expand the left-hand side, well, you're doing so at the mean of the transform variables, and that gives you at, that's fine, that's what you want. But the expansion point for the right-hand side is not q bar. It's not the time. It's not the time average of the original variable set. It's rather this thing q tilde, which is the nonlinear transform of the average rather than the average of the nonlinear transform. So we'll go beyond this issue in a couple of slides. But for the moment, let's discuss the equation that we get that relates this operator at to this operator a tilde, which is based on this q tilde. So what's interesting about this equation is the following. The second term, if the second term on the right-hand side is equal to 0, well, then you're talking about a similarity transform between a tilde and at, which means there's no change in eigenvalues, and then that's fine. So the conditions for which the second term on the right-hand side is equal to 0 is if you're talking about linearization about a fixed point of Navier-Stokes system, or you're talking about a linear variable transformation, in which case this disappears, you've got a similarity transform, and so there's no change in eigenvalues. The second term on the right-hand side is not 0, though, if you're linearizing about the mean, and you're talking about a nonlinear variable transformation. So that means that under those conditions, you may get a change in eigenvalue under the change in dependent variables that you consider. So that's between at and a tilde. As I said, we'd rather have a relationship or an expression giving us the relationship between at and a. It turns out that you can get a first order approximation to this by using a bunch of Taylor series expansions that I'll spare you the details of. But that gives you this expression, which is different from the one above in all of the red terms. And we don't need to get into the details of all of these terms, because basically what this expression is doing is it's confirming the fact that you don't have a simple similarity transform between A and AT once you're talking about linearization about a mean field and a nonlinear variable transformation, because this second term will be non-zero in those cases, as will this one. So this confirms that the nonlinear variable transformation may change the eigenvalues of the operator that you're using to analyze and model your flow. So that's the math. This slide just kind of wraps all of that up. It's a summary of it's a discussion of, I guess, what all of that means. So in summary, we're taking the Navier-Stokes system, and basically the point here is that you can obtain infinite arrangements of that system into a linear left-hand side and a nonlinear right-hand side, as we've seen from aeroacoustic analysis. All of those equations are exact. So that means, of course, that for each left-hand side, there's a unique right-hand side. And it means that if you do something to the left-hand side and you change it somehow, even if you're ignoring the right-hand side, you've implicitly changed the right-hand side. And the implication, of course, is that if you want to perform a physical interpretation without any danger, if you want a fail-safe interpretation, the right-hand side needs to be maintained. So I guess this is one of the reasons that in the title of this talk, there's a little plus next to linear, because These are linear analysis insofar as the left-hand side of the equation is linear, and very often we use that to do our analysis. But what we're showing here is that you can't just throw away or overly simplify the right-hand side. So analysis based on either the homogeneous system here or the inhomogeneous system, where you make a simplifying assumption about the forcing, that can be, it is ambiguous. These two final points, originally I didn't have these question marks because this was a kind of a gut feeling. The feeling was that the level of ambiguity might depend on the flow for the following reason. As I say, if you change the left-hand side, you're implicitly doing something to the right-hand side, even if you've ignored that. So the feeling was that this would be problematic in flows where you have a high sensitivity to forcing, which is characteristic of amplifier flows, and or where gain separation is low. And the feeling, for the same reasons, was maybe this would be less problematic when sensitivity to forcing is low, such as in oscillator systems. The reason I put the question marks is because since I wrote this down first, Uğur, the postdoc who's been driving this, has been toying with optimization schemes where he can find nonlinear transforms that allows him to manipulate the eigenvalues of the linear operator. And in fact, it looks like it's possible to turn an amplifier into an oscillator and vice versa. So that's something that remains to be explored in more depth. Here I'm on to the practical test case. So we were dealing with turbulent jets. That was the problem we were studying. And we're actually faced with an issue of a change from primitive to conservative variables because we were using a large eddy simulation that had been computed, and well, the various variables had been stored in primitive form, and we had a global resultant code which was written in conservative form, and so we had a compatibility issue. And so we used these databases to do a test of what the primitive to conservative transformation might produce in terms of problems. And so we decided to choose flows where there were large density gradients. That was something that we felt might lead to problems. Flows in which forcing details are important, so it's an amplifier. And the jet flow for certain frequencies are have optimal forcing modes that are extended in space, such that this homogeneous boundary value problem is a poor model. So we took a number of large eddy simulations that are numbered here 1 through 4. Basically, as you go from 1 to 4, we're increasing variable density effects either through an increase in compressibility or through a heating of the jet. So you would expect, as you move from jet 1 through to jet 4, that you get bigger issues with this transform from primitive to conservative variables. And indeed, that's what the results show. This table is showing a result for a given frequency. I think it's for Struhl 0.6. This is non-dimensional frequency. So for jets 1 through 4, this column here is showing the change in the leading gain of the resultant analysis as you increase variable density effects. You can have changes of up to 40% once you're talking about a compressible jet that has been heated. And this last column here shows you the difference in gain separation between the resultant analysis using primitive or conservative variables. And so again, gain separation is something that we're often interested in, because if you have a big gain separation between your leading resultant mode and the first suboptimal, that can be an indication that a low ranked model will be appropriate. So that's often something that we're watching out for in resultant analysis. And this shows that depending on whether you use primitive or conservative variables, you can have a change of up to 36%. And over a range of frequencies for jets 3 and 4, again, this is showing the change in the leading singular value. So that confirms that this may be an issue for compressible flows. This is the final slide on this piece of the talk, just some final discussion. So the takeaway message is that any mean flow based linear analysis depends on the forcing. I guess that's the key thing. Just as any acoustic analogy depends on any aeroacoustic analysis depends on the acoustic analogy that you use. So it depends on what way you've taken Navier-Stokes and broken it into a left-hand side and a nonlinear right-hand side. I've got a mention of eddy viscosity here because there's a lot of discussion of this at the moment in the literature, and I think this somehow clarifies what's going on when you use an eddy viscosity in your construction of your linear operator. Basically, you're moving something from the right-hand side into the left-hand side. Now that's fine. That can be an interesting modeling choice. But the point I'd like to make here is that there's no a priori reason why that would be the correct thing to do, right? It's something I think that any conclusion on whether it was a good idea or not should wait for a comparison with data. We're seeing that it very often does improve things. It can be a good modeling choice, but again, what it's doing is it's possibly compensating for a lack of modeling precision on the right-hand side by incorporating some of that nonlinear stuff into the linear operator. So all of this emphasizes, of course, that any linear mean flow analysis should be data-driven, and we need to pay closer and closer attention, I think to the forcing term. This is something that's happening. More and more teams are looking at the forcing term in detail to see how it works and how it might be modeled. And then the final point is that this ambiguity opens the door for optimization, because you can think about posing an optimization problem in this way. Let's find the split of Navier-Stokes into linear and nonlinear piece that would serve a particular need. You might like to enhance gain separation. You might like to align forcing fields with the leading forcing modes. So these are things that we continue to explore, and I think there will be interesting things that will come of this in the near future. Okay, that brings me on to the second part of the talk, where I'm talking here about how you can manipulate or tweak the resultant framework for the purposes of physical analysis or the elaboration of simplified models. I split this into two examples. The first comes from work that was led by Benjamin Bugea, who's a postdoc working with us on this European project. Co-supervised by Anurag Agarwal from Cambridge and Lutz Lesshaft from École Polytechnique in Paris. So these are some preliminary results from the analysis that we've performed so far. So we begin with the resultant system here. Q equals RF. This is Navier-Stokes rewritten in terms of linear and nonlinear pieces. You can read it as an input-output problem. And what we do here to begin is we tailor the thing to focus on a specific input and a specific output. So we're just redoing here things that have been done in the past by others. And in this piece of the slide, I'm just showing the difference between what I guess I call the standard approach and the modified resultant approach. You can write the system in terms of some observations Y by using this C matrix to localize what you call your output. So this could localize your output somewhere in space, or it could restrict it to certain of the dependent variables. The B matrix here allows you to localize the forcing. It says I'm interested in understanding what's happening at Y due to a forcing F that we localize somewhere else. So if C and B are both equal to the identity matrix, then we just have Q is equal to RF. That's the standard approach. And in that case, what you're doing is you're trying to maximize this Rayleigh quotient here, which gives you the minimal forcing that would maximize the response in terms of some energy norm that you define with this inner product, and that's what the singular values mean. So here you're trying to maximize global energy, typically. On the other hand, if we now use these matrices C and B to somehow localize what you call the input and what you call the output, we can create what I'm calling a modified resultant operator, or tilde. And in which case the Rayleigh quotient that we're now talking about is something that, well, we're trying to maximize this thing, which would find the minimal forcing in some region that maximizes an output somewhere else. So in this way, you can tune the framework to ask questions about an observable that you're particularly interested in. It could be drag, it could be fluctuating lift, it could be sound generation. The sound generation is the one that we were interested in here. So again, we're using these large eddy simulation databases provided, I should say, by Guillaume Brest from Cascade Technologies in California. These are databases we've been working with for nearly 10 years now. And so what we do here is we're going to localize the output in these rectangles on the outer side of the domain. That's what we call Y. So this is a region where the phenomena are purely acoustic. And we localize F within the jet. So we're looking to ask questions about what's happening in the jet that leads to the sound radiation that's observed far from the jet. And we're looking for a basis. What's the input-output basis that would be good for helping us to understand more about this phenomenon, and also for the construction of models of this phenomenon. So here we have examples of the leading response modes. On the top, you're looking at a mode that you obtain using the standard resultant analysis, where you're trying to maximize global energy. And what this tells you is that to maximize global energy, you need to generate a hydrodynamic wave packet. Here's the nozzle, this is the jet region. You see the saturated thing, which is a hydrodynamic wave packet. And in this case, for the maximization of global energy all over the domain, it looks like it's also leveraging some kind of pipe resonance. You can see sound waves that are issuing from the nozzle. On the other hand, if we look at the leading mode associated with the input-output, where we're interested in maximizing the acoustic energy irradiated by the jet, you see a change in the leading mode. In this case, what this is telling us is that if you want to maximize the radiated sound by the jet, again, you need a hydrodynamic wave packet, which is consistent with the work we've been doing for some time. And you also have this acoustic beam, which is now issuing from the jet. So this is an acoustic beam that's been generated by something in the jet rather than this resonance of the pipe. If we now move on and look at the leading forcing mode, so here on this slide, I'm looking at the standard resolvent. This is the leading response on the top. The forcing mode that would produce this is localized within the nozzle. So I've zoomed in here. And so what we're seeing is that it's pointing at an OR mechanism in the nozzle. And it's telling us that to maximize this response, well, you need to leverage here a non-normal amplification within the boundary layer, such that you get a maximum amplitude at the exit plane, and that of course kicks off the inflectional Kelvin-Helmholtz instability with a big amplitude, and it creates this big hydrodynamic wave packet. If we now focus on the acoustic resolvent, again on top I'm showing the response mode once again with its beam of acoustic energy. And if we now look at the forcing modes, it's pointing at two mechanisms. So this middle plot shows a zoom on the nozzle again. So once again, it's telling us that you would use the OR mechanism within the boundary layer to give you a high amplitude for the wave packet. But it's also giving us this supersonic wave packet within the jet. And this is something that we know from aeroacoustics as a very efficient generator of sound. If you have a wavy disturbance that's moving with the supersonic phase speed, it generates what's known as Mach wave radiation. And so this is another mechanism by which nonlinear interactions can drive an acoustic beam of this kind to maximize energy in the far field. So that's as far as you can go with I guess, the SVD of the linear operators that you build. But of course, to know what's happening in the real flow, you need to move on to the forcing. What you need to know now is how does the nonlinear forcing term project into this input forcing space so as to activate these different mechanisms. And so to push further to know what's going on, we need to access that forcing term. What we're discovering is that at low Reynolds number, you can do this with relative ease, but when you're talking about extracting forcing data from high Reynolds number, this is not trivial. And so this is now emphasizing the necessity for good data-driven modeling choices. And one such choice is something that's been explored by Ethan Pickering, who's a student of Tim Polonius in Caltech, where they're looking at how to manipulate the modeling of the left-hand side such that modeling of the right-hand side becomes trivial. So they try to introduce eddy viscosities that would allow you to assume spatial temporally white forcing terms on the right-hand side. So this is the wrap up of that piece. We're talking about tailoring of the resultant framework to provide a tool to you that allows you to ask questions about what's going on with the flow physics. It can provide input-output bases that are adapted for the given physics or analysis. It's useful for identifying physical mechanisms, but really to push this analysis to its limit, you've got to take into account the nonlinear forcing term. Hence again, the little plus in the title of this talk. And so to do that, as I said, you can either compute the thing and project into the input space. This is difficult, or an alternative, which is what the next part of this chapter discusses, is use of the target output to infer how that projection worked. So that's the second example. This is based on work led by Ethan Pickering, as I said, a PhD student with Tim Polonius in Caltech. Myself and Aaron Town are involved in this. And so again, this is the same framework. Let's begin with this equation. This is the resultant system written, so Navier-Stokes written in input-output form. And here already I'm talking about an acoustic output. We're talking about the jet again, and so Y has been localized in the acoustic region. So the OR I'm talking about here already has these C and B matrices that focuses the thing on the relationship between the jet and the sound field. We now write the thing in a statistical form, so you can compute the cross-spectral density of the sound field, that's SYY, and the resultant framework then allows you to connect that to the cross-spectral density, so the statistics of the forcing term through the resultant operator. If you then expand the resultant in terms of its singular value decomposition, this right-hand side is now showing you the machinery by which the statistics of the forcing drive the statistics of the output. And so all of the interesting stuff is happening in this inner projection where this structure of this thing projects into the input space. Now, as I said, that's a difficult thing to do for high Reynolds number systems. So what we did here, based on the observation that, well, we know that SYY is low rank. The sound field radiated by high Reynolds number turbulent jets has a low rank. So what that means is that the projection of these forcing statistics into the input space must produce something low rank, even if we're not going to look at the specific details of how this works. This produces a low-rank system. And so the idea here was to, rather than compute this inner piece, we would simply rewrite this equation in this form and set ourselves the objective of just trying to infer the structure of this inner matrix A. What is this matrix that combines the response modes to construct the cross-spectral density of the sound field? Okay, so these are the same equations again, just a reminder of what the true A looks like. And so what we do is we take this first equation and we rearrange it to identify the A by projecting the cross-spectral density of the sound field onto this response basis. If you do this for the full system, this remains an enormous matrix. For the problem we're looking at, this is like 10 to the power of 11. So what we want to do is reduce the rank of this. And there are a couple of steps that allow us to do that. Let me skip to the next slide to illustrate this more clearly. So the initial resultant modes are built using these big squares in the sound field. We then truncate the physical space down to these rectangles, which correspond to the region in which we have large eddy simulation data. So that's the first reduction that we do, which is discussed in this bullet point here. We reduce from R over D that spans from 5 to 20 to an R over D that spans from 5 to 6, and I'll call this Z. So we're going from the big square, which was Y, to these little triangles that I'm calling Z. Then by application of, that involves application of this matrix CZ both to the LES data and to the resultant modes that have been computed on the bigger squares, right? So that's the first truncation. The next truncation involves truncating the resultant basis to some small number of modes. So, you know, typically we'd like this value n to be less than 10. And that will provide us with a smaller basis that we're calling U tilde Z. Tilde corresponds to the basis truncation, Z corresponds to the domain truncation. Because of this truncation, we're going to lose orthogonality in the response basis. And so in order to evaluate this thing, we have to use a pseudo-inverse. And that's what we do here. So this is the Moore-Penrose inverse. And basically what this allows us to do is identify some matrix A tilde, which has gone from order 10 to the 11 to something which is of order 10. And again, this is on the basis that we know the output to be something which is low rank. So some questions we can now ask are, well, how well does this A tilde reconstruct the output stuff, the acoustic field and the rectangles of the LES, using the truncated basis, using this small object that we've obtained. We can then go and look at the structure of A tilde and try to figure out if maybe this can be further simplified. And then finally, of course, you'd be interested in how well this thing could be modeled in order to follow changes in, say, operating condition, Mach number, temperature effects. Okay, so this is a slightly busy slide. Let's go one step at a time. So on the top here, you're looking at data from the large eddy simulation database. Each of these squares shows information for different azimuthal modes. This is the axisymmetric mode. Actually, let's just focus on this. So this is the axisymmetric mode. These are spectra on vertical lines through this thing along these sideline, these grid lines that I'm showing here. So as you evolve downstream, you're seeing that the spectra become progressively energized and you have this low frequency peak in the downstream region of the acoustic field. And so what we're doing here is we're trying to reconstruct this information using this A tilde that we've identified. And down here, we're looking at models, one in which we use the molecular viscosity. This is for a subsonic jet. The other where we're using eddy viscosity. And as you go down along these plots, you're looking at changing the rank of this thing A tilde from 1 to 20. And well, basically what this is showing you is that with n equal to, I guess, 3, we're within a couple of dB of this thing. It's a little bit noisy, but I mean, we've got the main features. And so that shows us that we've identified a matrix which is small and useful for a description of the statistics of the field in the region that we're interested in. The other thing we see is that the eddy viscosity considerably improves things. So as I said earlier, eddy viscosity can be an interesting modeling choice, but you should wait to decide whether it was a good idea or not. You should wait until you've compared with the data as we've done here. This shows the structure of A tilde for different frequencies. Now bear in mind that a rank 3 model was useful, so we're talking about just the first 9 elements of this thing. This has been normalized to put 1 on the diagonal, and you can see that there's a kind of a diagonal structure to this. But an interesting question now might be, well, what additional things can we do to the linear operator in order, for instance, to completely diagonalize this thing? And maybe the variable transformation that I discussed in the first part of the talk could be an interesting tool to do this. Finally, in terms of modeling A, what we're looking at here are, sorry, this is a mistake. This should say A rather than B. What we're looking at here are the frequency dependence of those 9 entries of the first, that little piece of the A tilde matrix. Here you have the 9 entries. And remember, what A tilde corresponds to is this piece of the right-hand side of that first equation that I showed you. So it contains information about the projection, but it also contains information about the gain. Now, the gain is something that we can compute from the resultant operator. So we know what the frequency dependence of these things are. And so we can factor that out of this to produce this picture on the bottom right, which is showing some kind of interesting frequency dependence. This is a Strool to the -3 trend. And it turns out that this persists over a range of Mach numbers. So this is showing some properties, empirical, of course, but some properties of this A tilde thing that might allow it to be useful as some kind of empirical model to follow changes in operating condition. So that's the wrap up on that bit. It was possible to find a useful low rank matrix that can reconstruct the statistics of the thing we're interested in. There are some interesting empirical shapes. The Mach number dependence is being explored, and from what I've heard so far, as I say, this trend persists as a function of Mach number. Eddy viscosity was here found to be helpful. And I think further progress on this might come from further manipulating or tweaking the resolvent operator in order to maybe diagonalize this thing, for example. Okay, moving on, I'm now going to talk about state estimation. This is a piece of work that was led by Eduardo Martini, who was a PhD student in Brazil at ITA, supervised by myself and Andre Cavalieri. He's since become a postdoc in Poitiers, and this paper should appear soon in JFM. So again, the same system. I guess we can start with this third equation. We're here interested in some output in terms of observers. These could be measurements, and I'll specifically talk about measurements on the wall beneath the turbulent boundary layer. And so we can relate these things to the turbulent forcing once again through a resolvent operator which has been modified using these C and B matrices. Here the modified resolvent is being referred to as OR-Y. So the objective in this piece of work is to understand if from these observations, which could be experimental measurements, is it possible to estimate the force and the state. So To kick this off, the problem that's considered is, well, let's talk about an estimate of the force, where the tilde here refers to estimate, as a linear combination of the measurements or observations. And so we're interested in this transfer function TF that would map from your measurements to the force. And so the estimation problem that arises from that is, well, find the TF that would minimize the norm of this error covariance matrix, in which you have the resultant operator. This capital F here is the cross-spectral density of the forcing. So this is the statistics of the forcing are in here. And you have the transfer function TF. N, I didn't say, but this corresponds to the cross-spectral density of the measurement noise. And so in order to solve that problem, you look for a stationary point of this covariance matrix, and that basically allows you to find the transfer function TF. And this is the expression that you obtain. Again, this thing depends on the statistics of the forcing in F. It depends on the modified resultant operator that you can compute, and it depends on the measurement noise. Once you've got a transfer function that maps from the measurements to the forcing, well, then you can map from that estimate of the forcing to the state. And so that allows you to identify this transfer function TQ. So we've got a transfer function which allows you to perform estimation either of state or of forcing. The estimation is underpinned by three things. The first are nonlinear interaction covariance, so the statistics of the forcing. We require a model for that. It depends on how the nonlinear interactions map to the sensors or wise, so that's something that we can compute. And then how the nonlinear interactions map to the state through the resultant, the full resultant operator OR. So that's something for which we have a model. We did many tests. I'll show one here, which is based on a DNS of the channel flow. So we performed the DNS, the nonlinear covariance, which I'm calling F prime here. So this is the true nonlinear statistics. This is computed and saved with the data. The objective set here is to reconstruct near wall structures. So we're choosing these wave numbers, and based on measurements on the wall of these Fourier modes, we're going to try to reconstruct the full DNS information using the linear estimator, but of course it's linear plus, so it's a linear estimator which is being enhanced using information about the nonlinearity. So we test four models for the nonlinear statistics. The first is the identity, which is what's often used. And as if you do it this way, it corresponds to the most common use of the Kalman filter, I guess. So spatiotemporally white forcing. We consider a case where we use the zero frequency component of the true nonlinear forcing F prime, which means that we're talking about a temporally white but a spatially colored forcing. And then we use the true forcing, which should provide us with the best linear estimate that is possible to do. And there's a fourth one, which amounts to using an estimate of the forcing statistics using auxiliary sensors and an approach developed by Aaron Town during the CTR summer school a couple of years ago. Okay, so here are some results. Here we're looking at reconstructing streamwise velocity fluctuations at a y plus of 12. These are time traces. The DNS is shown in black. The green and red show what you get with the assumption of white forcing statistics. If you use the true color, you get the blue line, and you see you get a very nice match with the DNS. If I now look at a frequency spectrum, so this is power spectral density as a function of non-dimensional frequency. Again, you see that when you use the true color, you get a much better estimate of what's going on at y plus equal to 12. So by using the nonlinear statistics, you can improve the estimation substantially. These are now some movies from a follow-on work, which is being led by Felipe Amaral. He's working with André Cavalieri in Brazil, and all of these people are involved in this continuation of that study by Eduardo Martini. So this is the DNS. We're at a Reynolds tau of 180. We're looking at fluctuations of y plus of 15 here. And well, basically, if you use the true forcing statistics, apologies for the change in nomenclature, this PFF is what I was calling F. You see that you can produce a very nice match with the DNS. If you use an assumption of spatiotemporally white statistics, the structure is there, but the amplitudes are a little off, as we saw in the statistics earlier. If we now change to higher Y plus, you can see that again the true PFF is giving you a superior estimate in terms of the amplitudes of these things compared to an assumption of spatiotemporally white statistics. Okay, so I just last night got some results from a second simulation at Reynolds tau of 500, and we're getting similar improvements by using the forcing statistics to enhance this linear estimation. Oh, there's another one. This is Y plus at 90. So here you can see significant differences between the assumption of spatiotemporally white statistics and the use of the true forcing statistics. So again, this should give you the best linear estimate that it's possible to do. Okay, so that's a wrap up on that. Quickly, the resultant estimator has been produced that uses forcing statistics to enhance it. It's a non-causal estimation, which I should have mentioned. When you truncate it to its causal version, you've got something that's equivalent to the Kalman filter. And what this is showing us is that by using the true force statistics, you can get what should be considered the best linear estimation possible for a given number of sensors and positions of those. I didn't get into the details of how we compute this, but it's a matrix-free approach based on just one integration of the direct and adjoint equations for each sensor. So you can use this for big systems, basically, and for an experimental implementation. Okay, this is the final part of the talk. I'm sorry, I'm running a little bit long here, so I'll maybe get through this quickly. This is based on work by a PhD student, Igor Maya, who worked with us in Poitiers. He's now come back as a postdoc, and these people were also involved in this. Well, let me just skip on to the control piece of this. So basically, we're trying to understand if a linear control approach can be used in the turbulent jet. Here's the experimental setup where we provide ourselves with the possibility of driving the jet by forcing at the lip. Here we have synthetic jets. We have sensors placed downstream. This is a ring of microphones that allows us to extract different azimuthal modes. Actuators further downstream, these again are synthetic jets, and then we have a hot wire that we can traverse along the axis of the jet. These are the operating conditions, and we're going to subject the jet here to band-limited stochastic forcing, D. The control system works in this way. We consider the output, which is the measurement of the hot wire, as a linear combination of the sensors, which map to the output via this transfer function HYZ, and the actuator that maps to the objective by HUZ. In this experiment, we identify these transfer functions empirically just by looking at the cross-spectral density between the two things. But these, in principle, can be built from the resultant framework and indeed enhanced using what I described in the previous part of the talk. So we define the actuation in terms of some gain times what's measured at the sensor. This term here is a feedback term to account for contamination of the sensor by the actuator. And what this does is it avoids a Larsen effect. And from that, you can build the control kernel in frequency space, K, omega. And then by inverse Fourier transforming this, you have the control kernel in the time domain. And so the control law looks like this. You compute U as a function of T based on a measurement Y and its convolution with this control kernel. So these are some results. The three pictures show results for different bandwidth of the stochastic forcing. So what we're calling the baseline here is the blue curve. These are power spectral density measured by the hot wire at the downstream position. We force with different bandwidth, and so you can see the hump broadens. And the two colored, the red and the yellow curves show what we obtain when we implement a controlling that tries to attenuate, that's the red curve, or tries to enhance the fluctuations. So you can see, this is a log scale, you can see that we're achieving substantial reductions in a jet which is fully turbulent, and indeed the boundary layer has been tripped, so it's turbulent from the outset. There's a deterioration with increasing bandwidth, but we've identified this as something which is largely an actuator problem because the actuators are being driven at their limit and they behave non-linearly. Basically, as you put more and more energy into these things, the non-linearity becomes more and more severe. This just shows that further downstream, as we traverse the hot wire down to 7 diameters, which are the bottom plots here, the control effect persists, basically. So we're successfully performing wave cancellation control on a stochastic bunch of wave packets that have been seeded into the flow using a linear control law. What we'd like eventually to do, of course, is to control an unforced jet. And so to see how we might move in that direction, we here decrease the amplitude of the forcing that we introduced to the system from the green curve, which is what we used for the previous results, down to 0, which gives us the unforced jet. And basically what we see here is that this P is a measure of the control efficiency. So it's the reduction that's achieved. As you decrease the amplitude of the forcing that you introduce into the system, the control performance decreases substantially. And this is related to the coherence between the sensor and the objective, which is basically giving you a measure of how well the linear estimation will work. So when you've got coherence between the sensor and the objective of over 80%, your estimation is sufficiently good to be able to tell the controller what to do to get rid of the wave packets. As this coherence decreases, you no longer estimate with the same quality, and so your control authority disappears. And that's what this plot shows, that as you reduce the disturbance amplitude, you reduce this coherence, so you're degrading the transfer function from sensor to objective, and so your control authority decreases exponentially for a bunch of frequencies. So final slide on that. What this is showing is that where control of an unforced jet is concerned, it's really a question of the coherence both between sensor to objective and actuator to objective. And so what we've done here, just to explore what might be possible by changing sensor positions, is we've taken data from a large eddy simulation data, and we're basically looking at how the coherence between a sensor point shown by this red dot and every other position in the domain varies. And what this is showing us is that for certain positions, for example, this one here, you can get coherence in the natural jet of order 80% over maybe 2 diameters, which would be sufficient for the implementation of this kind of control in the unforced jet. So this is suggesting that by improving the actuators and being better in positioning the sensors, it should be possible to reproduce what we've done for a stochastically forced jet in an unforced jet. Okay, so that's the conclusion on that one. I'll jump straight to the main conclusions. So I'm talking about linear plus modeling of turbulent shear flow. We continue to see this framework prove its merits for modeling, for the analysis of physics, and for estimation and control. Its use and interpretation is clearly less straightforward than it is in transition applications because of this mean flow issue, right? We're not talking about a linear operator constructed about a fixed point. It's being constructed about the mean, with all of the problems that brings with it. Attention has been largely based on the linear operator. We're now seeing that it's clearly important to look at the nonlinear forcing term, and as I say, there are many people doing that. This is something which is challenging, particularly at high Reynolds number. But I think by combining and leveraging numerical simulation theory, these new tools and experiment, we can expect big progress in the near future. And experience from the aeroacoustics community will probably be valuable given the parallel between resolvent analysis and acoustic analogies. And with that, I'll stop and apologize for being a little bit long, as I say. So back to Sean and David.
Yeah, thank you very much for that very nice talk. If people have questions, could they please either raise their hand or post a question to the group chat, and then we can figure out the order of who gets to ask when. I see Daniel has a question. Daniel, can you go ahead and unmute yourself?
Thanks. Hi, Peter. I thought I'd just start you off with a pretty simple question. I think I just missed this. In Ur's work, when you were saying that you think it would be the stronger the density gradients, the more this issue of ambiguity might arise. We're talking about the hot jet had that much greater effect than the equivalent jet at the same Mach number. Is it the mean density or the fluctuating density that's driving that?
The mean density.
So it's the mean density. Okay. Right. Like I said, straightforward question. Thank you.
Thank you. I see.
let me think about that again. It's the mean density, but insofar as the fluctuating density can play a role in the rho u term in the conservative formulation, you possibly have a role from the fluctuating density also in its correlation between rho and u. So you possibly have a contribution from both.
Okay, thank you.
I think Vasily had a question.
Yeah.
Hi, Peter. Thanks for a brilliant talk, as ever. I did notice that you mentioned that we need to pay attention to, of course, to the nonlinear term, and you have access to, say, databases generated by DNS and or LES and or some experiment. Can you please make some comments regarding the modeling coming from runs?
Sorry, do I have comments on modeling coming from runs? Is that the question?
Yes. I mean, what role does runs play in all this? To what degree do you need the access to the nitty-gritties that you can extract out of LES or DNS, but you cannot extract out of runs? You have a priori model.
Yeah, so the rounds, I think, is primarily useful for providing mean flows on which you can use to build a linear operator. But in terms of the nonlinear term, rounds is not going to give you what you need. Indeed, we're discovering that even LES is struggling to give us that F with sufficient accuracy. And there's another issue, of course, which is that all of the equations that I've shown are associated with the Navier-Stokes system, whereas LES data is associated with filtered Navier-Stokes system. So you have an immediate incompatibility between the forcing term that you would compute from a large eddy simulation and the resultant framework, which has been constructed using the full Navier-Stokes system. We're not writing the resultant problem out in terms of the large eddy simulation equations, where most people are writing it out in terms of the Navier-Stokes system. So that's one issue, but there are many others. One that's probably worth mentioning is this CSD, the cross-spectral density of the forcing statistics. This, you're talking about 2-point information. This is 2-point fourth order statistics you're talking about. So it's very difficult to converge this thing. We're talking about running large eddy simulations for 2000 convective time units, which is much bigger than what most people would usually do. And even with those lengths and the size of those databases, it's not a trivial thing to converge these statistics. Then you have issues associated with the grid on which you store the data. Very often you have interpolation, which adds interpolation errors. We're discovering that there are issues associated with aliasing because the forcing term is something which is a DDT of the state variables. And so you've got a multiplication by frequency. So the forcing quantities have a much higher frequency content than the state variables, which means that places limits on the, what you would have accepted as a good sampling frequency for a correct spectral description of the state variables is not sufficient for the forcing. So there are a number of practical issues which are making this forcing term extremely difficult to extract from high quality large eddy simulation. So far, I think taking it from DNS at low Reynolds number, that's okay. Finding it from at higher Reynolds number is a real issue that we're going to have to figure out.
Thank you.
I see there's another question in the group chat. Could you please go ahead and unmute yourself and ask your question?
It's an LES question, it looks like.
Yeah, it's an LES question. Let's see, LES. I don't quite understand the question. In the meantime, I have a quick question, actually. Peter, when you were showing the plots with your collaboration with Ethan, Aaron, Tim, reconstructing the jets, I think, cross-spectral densities, I was wondering the eddy viscosity that you used, was that just used across all Struhl numbers and azimuthal wave numbers, or was it specifically optimized for the parameters that you were looking? Because I know that Ethan's been optimizing it across azimuthal wave numbers and different Struhl numbers. So I was wondering, is that eddy viscosity uniform across all of those parameters, or is it a function of those parameters?
I'm not entirely sure, Sean. I think in what I'm showing, it's uniform across those parameters, but to be honest, I'd have to ask Ethan how exactly he did that. I can't remember. I'm sorry.
Yeah, no worries, no worries. Let's see. Trying to, where is this person? Does anybody else have any questions? Oh,
yeah, I do have. Yeah.
Yes, please go ahead.
Yeah, I would like to ask a very simple question. Like, let's say if we solve large simulation with grid resolution less than Kolmogorov length scale, like, what will happen? Like, theoretically, the subgrid stress term or subgrid stress modeling will have no contribution in the solution, right? Now, how about the error related to the dissipating error? Like, can you please elaborate this one for me?
I guess it's a bit hard to answer that question with a definite answer. You know, the errors associated with the subgrid modeling it's only one source of difficulty. In fact, I guess what I was saying a moment ago to Vasily is that the point is that we're encountering about 4 or 5 different sources of error when we try to do this, ranging from interpolation error to aliasing error, to convergence issues, to the incompatibility between the LES and the DNS. So it's hard for the moment to say how much each of those errors is contributing to the overall difficulty that we're
How about
facing.
simple laminar flow? Let's say I apply LES with Kolmogorov length scale, like very fine mesh in simple laminar flow.
Yeah, in a simple laminar flow, there's no problem. And in fact, even in low Reynolds number turbulent flows, there's no problem either. There's a paper recently by Petronio Nogueira, Andre Cavaliere in the KTH group, where they're, I think, looking at the nonlinear term from a low Reynolds number channel flow. And in that case, they're able to compute this thing without any issue. And then they don't have all of these problems. The difficulty is at high Reynolds number turbulent, in high Reynolds number turbulent flows.
Thank you very much.
Anybody else have any questions?
I do have one.
Yeah, go ahead, Petronio.
Well, thanks, Peter, for the amazing presentation. Concerning this expansion in the first part of your presentation, actually, I was just wondering which would be the real expansion, like the one that we would find in experiments. Because if there's this ambiguity, then which case to choose? Which mean flow to choose?
I think that's an open question. The point is that you can, well, I guess maybe there are different ways to answer that question. The point is that whatever linear operator you choose, there is a nonlinear term that goes with that thing that you can't ignore. So provided you always maintain the 2, in principle, you've got no problem. The difficulty, of course, is that you can't get the right-hand side all the time with good accuracy. So, you know, the answer as to what way you should construct your linear operator, I guess you should build it in a way that you get a best match with your experiments. So you could either, you know, you could build it such that this is what Ethan and Tim are doing. They're trying to optimize that thing such that the modeling of the right-hand side becomes trivial. They would like, you know, the modeling of the right-hand side to correspond to some sort of stochastic forcing. And in that case, what's happened is that you've compensated for all of the color and all of the interesting things about the forcing. you're somehow incorporating that modeling into the linear operator. And that may be an interesting thing to do. But of course, if you're then interested in trying to understand the details of how the nonlinear interactions do what they do, you've probably lost that information. So I think it really depends on what it is that you're trying to do. If you're looking for a detailed understanding of the nonlinear interactions, it's best to use a molecular viscosity and leave the right-hand side as it is. Whether you use primitive or conservative shouldn't matter if you have full access to the right-hand side. You see what I mean?
Mm-hmm. That makes sense. But well, for the resultant analysis, that will be quite clear because you do have a forcing. But when you do that for stability analysis, for example, you are in the end incorporating some of the nonlinearities inside your operator, right?
Yeah. Yeah, of course. But you know, even in Crichton and Gaskell's statement, that's kind of what's already being said. You've incorporated for some of the nonlinearity by considering that the turbulence has generated the mean flow. So this modeling, that's why it's linear plus, it's linear, but the nonlinearity is always hiding somewhere in the background. The question, I guess, is how explicitly you bring it forward and how you decide to deal with it, depending on what your objective is.
Nice. Okay. Thanks a lot.
Thank you for your question. I think we should conclude it there and let. Whoops, my light just turned off. And let. I think this is a good place to stop. Thank you once again for waking up very early and giving us this very, very interesting seminar. And I'd like to thank everybody for attending and asking questions. It always makes for some good discussions at the end. So.
Okay. Thank you, everybody. I'm now fully awake, thanks to you.
So thank you, everybody, and we'll see you next